So chapter 2, we started talking about last time, really sort of getting into a little bit of dimensional analysis and conversion factors and equalities. So remember that any equality is really kind of two different values on two different units, but they do represent the same amount of anything. So again, if we had 12 inches, that represents the same as 1 foot. And that is what's considered an equality. From any equality, we can, as we talked about, really write two conversion factors. And really the conversion factors are just simply fractions, where one unit is up on top and the other unit is basically on the bottom. Or if you need it the opposite way, you can set it up, in that sort of fashion. Now, when we do use conversion factors, as we talked about, we really will pretty much just use one of them at a time. And it really does depend on sort of what you're looking for. The idea is we sort of want to get rid of the units we don't want and sort of end up with the units that we do want. And we do this by really what is referred to as dimensional analysis. Or sometimes people just call it problem solving. But the idea really behind dimensional analysis, and why, as we did some examples last time, that you really should always show your work this way, is that it really does allow you to sort of follow what's happening with the units and the units you want to get rid of. So the general idea is, if you have a specific unit that you do not want, you basically put that same unit in the opposite location, and you put the unit that you do want a lot of times up there on top, for example. And again, these guys will cancel each other out, and that will leave you with the unit that you're looking for. Mathematically, as we talked about, what we're doing is we're multiplying whatever's on top, and we're coming back and dividing by whatever's on the bottom. So for example, if we had 425 inches and we want to know how many feet that was, we would start with 425 inches. Once again, it's not written as a fraction, but it is assumed that the inches are up on top. And that tells us when we do go to our sort of conversion factor here, we would want to use it where inches are in the opposite location. And we would do 12 inches on the bottom and 1 foot on top. So just like when you divide two numbers that are the same, it equals 1. When you divide two units, one on top, one on the bottom, is the same. They basically cancel each other out. So here we would multiply basically 425 times 1, and then basically come back and divide by 12. So basically 425 divided by 12 gives us this number on the calculator here, 35.41666666. Lots of sixes, sevens, something like that. And the units here would be feet that we are left with. Now, in terms of the significant figures, we also talked a little about, there is, again, a reminder, we have basically English to English conversions, or US to US. We have metric to metric conversions. And these are both considered really exact numbers. And as we talked about, if it is an exact number, you don't have to worry about it in your calculation. You basically ignore it because it could have multiple amounts of significant figures. It's really only, as we talked about, when you cross over kind of metric to English, if it's not like an exact conversion, like 1 inch is exactly 2.54 centimeters, you should look at the equality or conversion factor that you use. So in this particular case, that's inches and feet, which are both English to English conversions. And that means that this is considered an exact number, which means we do not have to worry about it. So we would default back to our original number here that has 3 significant figures. And one of the nice things about sort of dimensional analysis is you're pretty much always doing multiplying and dividing. That's all you're doing. So you're always going to be looking at significant figures here. That means our answer really should have 3 sig figs, which takes us to about there. And we should end up with something like 35.4 feet in this case. Yeah. Any questions on any of that stuff that we kind of talked about last time there? We also, I think, did an example or something like that where you got units on both up and bottom. So again, setting it up with this dimensional analysis where you can see clearly where the unit is will really allow you to, you know, hopefully solve it correctly. Any questions on that there? Okay, so why don't we try this here? A doctor ordered a prescription of a doses of 0.15 milligrams. If you have only 50, and that is micrograms, again, an interesting unit there. It's micrograms. Tablets in stock. How many tablets are required? So why don't you take a moment here, and then we'll go through it. And again, micro is 10 to the minus 6. So micro is 10 to the minus 6, or I guess how they do it, MC. And milli, right, is 10 to the minus 3 as well. Okay, let's take a look, see how you're doing. I think it's worked out for you, but let's take a better approach maybe to solve this problem. So we're basically looking for how many tablets that we need. We actually are given basically this, which is a conversion factor within the problem that basically says for every 50 micrograms, that's basically 1 tablet. Or basically 1 tablet is 50 micrograms in this particular case. So in this case, we could use it either way, coming basically from the problem. This is how much we want to give, which is actually in milligrams. So our problem, though, right, is that our grams are not in the same gram unit, right? One's milligrams, one's micrograms. So you do need to do a conversion. So remember that you can go to a table and you can find these conversions basically on the table, and we could use those to help us out here. In this particular case, you could either convert the milligrams to micrograms or the micrograms to milligrams. It really doesn't matter. Since this is just by itself, what I'm going to do is actually convert this guy into micrograms. And once I do, then I'll be good to go with one of these conversion factors really to solve the problem. Now, we also talked about this last time, kind of going from prefix unit to prefix unit. The best approach is to take it from micrograms to the base unit, which is grams, and then take it from grams to milligrams. And that's because you could go to that table like we talked about basically and find those conversions pretty easily, rather than maybe trying to figure out, you know, what is the direct route between milligrams and micrograms, you know, what should I move? So that would be my recommendation to do that. We're going to take 0.15 milligrams and we want to convert it into grams. So a reminder that when we see something like this off of that table, in this case, that means in 1 milligram, there are 10 to the minus 3 grams. So again, that is the proper way to use that table value. And that means that we do want to go opposites. So milligrams are on top. So we do want to put milligrams on the bottom. We would go with 1 milligram on the bottom and 10 to the minus 3 grams up on top. At this point, if I stop my calculation, the milligrams would cancel and I would be in units of grams. Any questions so far? Now that's close to what we need, but we do need to get it to micrograms. So once again, we could go to the table and we can find the micro conversion. And in this particular case, once again, what this means is in one of the prefix units, in 1 microgram, there would be 10 to the minus 6 grams of the base unit. So again, I think we talked about a number of times that people very commonly kind of reverse those numbers and use it incorrectly. Now, because I set this up with dimensional analysis, I could clearly see that the units of grams are up on top. So to make it cancel, I actually need to put the grams on the bottom. So that would be 10 to the minus 6 grams on the bottom is 1 microgram up on top. Grams will cancel. Any questions on that setup there? Now I grab a calculator. So once again, we're going to be multiplying what's up on top and coming back and dividing by what's on the bottom. Remember, when you see 10 to the minus 3, that represents 1 times 10 to the minus 3. So again, you can put it into your calculator in scientific notation, and you should be good. We'll go 0.15 times 1 times 10 to the minus 3, hit equals. Making sure you use your exponent button. Dividing by 1 to the negative 6 gives me 150 microgram doses is needed. This technically is an exact number, so is this, which means this guy's got 3. So we do want to kind of maintain the decimal point there at the end of that. First off, any questions so far? The purpose of this is to get it into the proper units, because now that it's in the proper units, we could use one of our conversion factors that we had from the actual problem. In this particular case, we would take our 150 micrograms. And which conversion factor should I use? The one on the left or the one on the right? So which one of these should I use? The one on the right will cancel it out correctly. We want to get rid of micrograms, which are on top. So this would give us 50 micrograms per 1 tablet. And that means that technically speaking here, you want about 3 tablets basically given to the person. So I put 3.0 for sig fig purposes. The book might just use 3 because it's a whole tablet. You know, it's something that would be counted. But technically speaking, sig fig wise, that has 3 sig figs. This is not an exact conversion, so that one would have 2 sig figs based off of that. And that is how we get to really 2 sig figs there at the end. Yeah. Any questions on that there? Now, the worked out part, they went directly from milligrams to micrograms. Again, I would highly recommend not doing that. I would go back to the base unit and then to the next prefix unit. Probably less room, hopefully, for error. Any questions on any of that there? All right, let's take a look at another one here then. They agree, 3 tablets, so that's good. It's nice. All right, forget about minutes and days. We'll skip that one, actually. Let's do this one. If your pace on the treadmill is 65 meters per minute, how many minutes will it take you to walk 7.5 kilometers? The kilo prefix, 10 to the 3. All right, so take a couple minutes there, see what you come up with here. See how you're doing. So we got a couple of things here. We have this, which is really a rate. And a rate is really your distance per time, right? It's your rate. And we also have our distance that we want to travel. And we really want to know how much time it's going to take us to do that. So it's really the rate that's going to allow us to do that. And we can use that as a conversion factor. We could say in 65 meters, it will take us a minute to do so. Or we could flip it around, in a minute, it will take 65 meters to go. Our problem, though, is our distance here is in kilometers, but in our conversion factor that we're going to use, it's in meters. So we do need to do a conversion. And once again, you could either convert the meters to kilometers, or probably a lot easier, just convert the kilometers into meters. So we will use our kilo conversion here. And in this case, it means in one of the prefix, so in 1 kilometer, there is 10 to the 3 meters. So once again, that is the proper way to use that. That gives you 2 conversion factors, 1 kilometer over 10 to the 3 meters, or 10 to the 3 meters over 1 kilometer. So the first thing we want to do is get everybody in the same units. So 7.5 kilometers. Once again, dimensional analysis here, we see kilometers are up on top, which means we need it on the bottom to properly cancel it out. So we'll use the guy on the right, and that will give us 10 to the 3 meters over 1 kilometer. And again, that 10 to the 3 is 1 times 10 to the 3, or really 1,000 is the same thing. We're going to multiply basically by that. There's really nothing to divide on the bottom. The kilometers will cancel. and that will give us 7.5 times 10 to the 3 will give us 7,500 meters. So now that we have the distance in meters, that's going to allow us to use our conversion factors to really answer the question, to go from distance to time is what that's going to allow us to do. And if we just think about units here, 7,500 meters, once again, we go on to get rid of meters. So we will use the conversion factor here on the right to do so, puts meters in the opposite location. That leaves me with minutes and 65 meters. The meters here will cancel. We're basically going to take 7,500 and divide it by 65. Will give us 115.3846154. And the units here are minutes, which is good because that is what we're looking for. Not good is our sig figs here, right? So what should we end up in terms of significant figures? We should end up with 2. So if we look at our first part of the calculation here, that has 2 sig figs. This is an exact number, so you don't have to worry about it. That means over here, that's 2 sig figs. And this guy has 2 sig figs, which means 2 sig figs actually should take us to there. We do need a round because the next number is a 5. So that's like a $1.20, 120 minutes. Yeah, no decimal. Any questions on that? So as we talked about before, a lot of times you will get sort of conversion factors that you can use in the actual problem. You do have to usually look at the significant figures that are in those because they're not really exact numbers. Any questions on that one there? Okay, let's try a couple more here just to make sure they agree. That's good. All right. All right, let's try this one. You go to the local AM, PM, you decide to hit the Thirst Oasis. Lots of good stuff there. Too much, they say sometimes. You decide to buy 32 fluid ounces of Diet Coke, crushed ice, cubed ice, whichever it may be. How many gallons of Diet Coke did you drink? Here are some equalities that might be helpful and the respected conversion factors. So figure out how many gallons you drank, set it up using dimensional analysis so you can see the units and see what you come up with here. Okay, let's take a look. So once again, we want to go from fluid ounces in this case to gallons. You do want to kind of think about a pathway to get you there. And I chose these equalities and conversions to do it. I'm going to go from fluid ounces to quarts and then quarts to gallons. As we might talk about last time, you know, there could be multiple ways you could get to the same result depending on the conversion path you choose. As long as they're legitimate conversions, then they all should be okay. Now, obviously, from the first equality here, these are the 2 conversion factors that we could use. And from the second one, these are the 2 conversion factors here that we would use. Starting with our 32 fluid ounces. Once again, here we want to go opposite. So fluid ounces is up on top. So we will use the conversion factor here on the left that puts fluid ounces on the bottom, and that is 32 fluid ounces is 1 quart. If I stop the calculation right at this point, the fluid ounces will cancel, and that will leave me in units of quarts, which is close to what I want, but not really what I want. So I do need to do obviously the next conversion. But I could clearly see that the quarts are up on top. So once again, to get rid of them, opposite to do that means we need to use a conversion factor there on the right to do so. And that's going to put 4 quarts there on the bottom and 1 gallon up on top. The quarts here will cancel. Once again, we're going to multiply across the top, which is basically just 32, and then divide by 32, hit equals, and divide by 4. And we will end up with 0.25 gallons of Diet Coke we're drunk. In this case, sig fig wise, you would be defaulting back to our original number, as these guys here would be considered exact numbers, so you don't have to worry about them. The correct answer is 0.25. The wrong answer is 1/4. Because 1/4 makes me think you're too lazy to divide. Yes, so never give a fraction for an answer. Like I've had people give, 335 miles over 625 hours and circle it. Don't ever do that. Yeah. So divide it out, get a number. Don't leave your answer as a fraction. Any question on any of that there? Okay. So again, it's really important, as we've been talking about, to set it up this way so you can see the units cancel. Again, it does hopefully help you not make any sort of calculation errors, divide when you should multiply, or vice versa, which is, again, a common error that sometimes people make. Any questions on that one there? Yeah. All right. Hope he agrees with me. Good. All right. A patient receives 5 pints of plasma. How many milliliters were given? Again, here's a few conversion factors and equalities that might be helpful. So take a moment here, figure out how many milliliters were given. Okay, let's take a look. So again, you want to think about a pathway that will get you there. So we're starting with pints. We want to end up in milliliters. So based on what I chose, I can go from pints to quarts and then quarts to milliliters to get me there. These are going to be the 2 equalities that will allow me to do so. And from each of these equalities, these are the 2 respected conversion factors that you could use. So here we would start with our 5 pints. Once again, not written as a fraction, but basically pints are up on top. So that helps us understand that we should use the conversion factor here on the left. That puts our pints in the opposite location, which is on the bottom, and 1 quart. Once again, at this point, if I stop the calculation, my pints would cancel. I would be in units of quarts, which is halfway to where I need to go. So once again here, so we can see that the quarts are still up on top. That means that makes our choice for conversion factor pretty simple. We're going to use the one where the quart's in the opposite location, which is on the bottom. And again, we're going to set it up that way so we can see it. 1 quart on the bottom, 946 milliliters up on top. Once again, the quarts will actually cancel each other out. We're going to then multiply everybody that's up here on top, and once again, come back and divide by what's on the bottom. And if I do that, that is 5 times 946 hit equals, divided by 2 hit equals. That will give me 2365 milliliters. First off, any question on the setup there? Now let's talk a little bit of significant figures. So let's start with our conversion factors here. Should I worry about the sig figs in this one? The answer is actually yes, because that is a metric to English conversion, which means technically you should look at this number, which is 3 significant figures. This one I do not need to worry about because it's basically English to English. And this one I should worry about, which is 2. That means my answer should end up with how many significant figures? Should end up with 2. Again, we're just multiplying and dividing. So we're looking at the number of sig figs, and the one with the least number of sig figs is what we're shooting for. That takes us to here. We do need to look at the 6 next to it. It means we need to round up, and that's going to lay us up a 2,400 milliliters. Or if you wanted to do a little scientific notation for old time's sake, 1, 2, 3. I don't know how old it is, but you can do that. All right, lower that. Any questions on the calculation, the sig figs? No? Okay. All right, let's try one more here to wrap up our conversions and dimensional analysis. We decided that we are trapped a long way to go here. There we go. All right, we are stranded 125 miles away from home, no money. Seems like a nice day outside. Actually, it got really cold earlier today when I went outside. It seemed really cold when I got out of the car. If you walk an average of 55 feet per minute, how many days will it take you to get home, provided you never stop? All right. So there's some conversions that might be helpful. See what you come up with. Again, this is like one we did earlier. We got like a rate, right? We want to end up with time. So think about, are our distances in the correct units or not? So very much like the last one, we're really given a rate here as a conversion factor that we can use in the problem. So we could use it the way I wrote it there, 55 feet per minute, or if we needed, we could have minutes up on top and 55 feet on the bottom. This is really our distance that we want to travel. And once again, our distances in miles are kind of rates in feet. So you got to choose one or the other basically to get it to the same units. So I'm going to convert our miles into feet, and then I can just use the conversion factor the way it is. So I'm going to take my 125 miles and convert it into feet. I'm going to use this equality to do so. And once again, we're going to go opposite. So I want 1 mile on the bottom, so it cancels, and 5,280 feet up on top. And once again, the units will cancel. So we're going to multiply 125 times 5280. Going to give us something like 660,000 feet. I think I got all the zeros there. Now that I have the distance in the same unit as my rate, I could just use the rate as a conversion factor to really go from distance to time. So that's what that's going to allow us to go, because we do want to end up in time, which is how many days it's going to take us. So a little 660,000 feet. You definitely get all your steps in that day. All right. So we're going to take our rate and we want to go opposite here. So feet are up on top. So using sort of the conversion factor that way, we'll put the feet on the bottom. And by doing that part of the calculation, the feet will cancel. And now I am in units of minutes, which is units of time. And that is ultimately where I want to eventually end up as time. Any questions on that so far? The rest is just now to take a conversion from minutes to days. So you see in our unit up there on top, we hopefully know there are 60 minutes on the bottom to cancel in 1 hour. So again, the minutes will cancel. And if I stop right here, I'm in units of hours, which is close to what I want. Once again, I can see hours up on top I do not want to keep. So that's going to be 24 hours in 1 day. Hours here will cancel. Days will be left there by themselves. We're basically going to take 660,000, and there's really nothing to multiply it on top. It's all ones. Hit equals, if you did multiply it, divided by 55, hit equals, divided by 60, hit equals, divided by a 24, hit equals. And that's going to get us like an 8.3 days is going to take us. Nice leisurely walk, great days, yes. Provided you don't stop, I suppose, yes. Any questions on that there? Now, setting it up this way is really important because I can't tell you how many people will do this problem and frankly will multiply by 60 and multiply by 224 because they don't know really where the units are. And it's a super common error. So if you set it up like this, it keeps it very simple of, okay, I just need to put it in the opposite location, right? And you should be hopefully okay. Once again, multiplying everybody on top and always dividing anything that's on the bottom. And once again, as we also talked about, you want to avoid punching all these numbers in at once in your calculator. You might end up with the wrong answer. So you can multiply as many numbers as you want that's on top. Then you could come back, divide by the first number, hit equals, divide by the next number, hit equals, and so forth. And you usually will get the right answer. Now, I did most of these conversions all in sort of one step or one calculation. And if you don't want to do it in one calculation, you can do it individually, kind of do the first conversion, then do the second conversion. If you do it individually and get a number and continue on with that number, you should definitely wait on rounding till the very end and just kind of clean it up at the end. By the way, cleaning it up at the end means in this case, we should end up with what I wrote there, I hope. Otherwise, that's not so good. We don't have to worry about this one, exact number, exact number. We do need to worry about this one. That's just from the actual problem, which means 2 significant figures. And really, although I did not write it correctly here, this number really had 3 significant figures based off of that is what that should actually be. And really the 2 sig figs is actually coming from the 55, the way I wrote it there. I don't know if you had 55.0 on yours, did you? No? Okay. I change it sometimes. But technically, since I was continuing on, I didn't do any real rounding here of anything like that, but I did keep track in my head of it really is 3 sig figs, which means when it got down here, it really is 3 sig figs. And then really we had 2 there that we should end up with. Question on conversion factors, equalities, dimensional analysis, how to set it up. You should, if you want full credit, which I imagine you do, need to set it up like this. Yes, with the dimensional analysis, the units and all that kind of stuff. Any questions on any of that there? All right, so to finish up this chapter here, we're going to talk about density next. I hope. Feels like we're getting to the end of this never-ending chapter. All right, so density of an object. The density of an object really will determine in a lot of cases, for example, if something will sink or float in water. So if something is more dense than water, it will sink. And if something is less dense than water, it will float. And by the way, the density of liquid water is 1 gram per milliliter or 1 gram per cubic centimeter. So if you ever find yourself like, I feel like I need the density of water to solve a problem, pretty much 1 gram per milliliter is the density of liquid water and most people use. The truthful answer is it really does change with temperature, but in most cases, that is pretty much the value most people use in most situations. So you can see here, these guys are a little bit less dense than water, so they're floating. These guys obviously are more dense than water, so they are sinking. If I take like a sink of water or a tub of water, and I take my Diet Coke can and my regular Coke can, and I put them in, what happens? Do they both sink? Do they both float? One sinks, one floats. This is what happens. Coke sinks. Diet Coke floats, right? So why does Diet Coke float? Yeah, pretty much it has artificial sugar, right? And real Coke has sugar. So it makes it heavier and it sinks. Good party trick in case you ever do it. I know Super Bowl was yesterday, but good party trick in case you ever want to do that. But yeah, so Diet Coke obviously has artificial sugar and doesn't really have sugar, so it's actually less dense. All right, so when we do calculate the density of an object, we do compare the mass to the volume. So the formula for density is mass divided by volume. And you do need to be able to kind of rearrange this equation because we do solve for all 3 of those things. If we want to solve for the volume, it would be the mass divided by the density. And if we want to solve for the mass, it would be volume times density. Some people remember the DMV triangle. Everybody loves the DMV. Unless you're going to the DMV, maybe. I don't know. It's good times. All right. So density is mass over volume. Volume is mass over density, or mass is volume times density. There's 2 common units of density that we really do come across. And as we saw there a second ago, for water, it is grams per milliliter or grams per cubic centimeter are typically the units we associate with solids and liquids. And a reminder that a milliliter is the same thing basically as a cubic centimeter. So in terms of the volume, and these all both represent volume basically, right? And that is why it's mass, which is grams per volume, which is something like milliliters. To get the milliliters, very commonly, you could just like take a reading, right? Fill something up in a graduated cylinder, take an actual volume reading, read the bottom of the meniscus. To get something like cubic centimeters, you could take 3 length measurements, like length times width times height. And once again, if they're all in like centimeters, when you multiply them together, you get cubic centimeters, which again is a volume, while each of these individual measurements are lengths. When you multiply 3 of them together there, you can get a volume. So that's a very common way. For example, if you had like a kind of solid square wood block or something like that, you can measure those 3 dimensions and multiply them together and get the volume of the wood block. And again, if you're dealing with something like a liquid, you can just take a volume reading. Speaking of liquids, if we have liquids with different densities, they will, right, separate out into sort of different layers. The least dense liquid would be the one on the top, right? So that should be the less dense, right? More dense. You throw like an eggshell or something in there, it gets caught right about there, for example. That means this guy is less dense than everybody below it, right? And more dense than what's above it, basically. And stuff like that. Any questions on that there? All right, so a couple of things about density. Typically speaking, in terms of phases, most substances in their solid phase are usually more dense than their liquid. And that's because in the solid phase, everybody packs in really tight to one another. They're very dense, so they usually have more density. Major exception to that is something we see every day, which is water. Yes. When I put ice in my cup, it ends up where? Yeah, it floats, right? So ice is actually less dense than liquid water, and that's a very different sort of thing. So ice actually is less dense than liquid water. That's why ice cubes float. And really the reason for that, we'll talk about maybe in a later chapter as well, is when all the water molecules basically come together in their solid phase, because of the way they bond together, they actually create a big open space between the different water molecules. So as they come together, they actually can't get together super close to one another because of the way they're bonding. And it creates this really big open space. And if you think about the density formula, density is mass divided by volume. Because there's a lot of empty space, that means the volume of ice is very large. So the bottom number would be a big number, top number would be a smaller number. You end up with actually a lower value of density than you do with liquid water. Because they haven't really locked into place in liquid water, there's still room for movement. So they actually can get the water molecules closer to one another. And again, that's an unusual sort of characteristic. Again, most things in their solid state are usually more dense than in their liquid state. Although we don't get too much into density of gases, they typically are given in grams per liter. If you ever come across the density of a gas, a lot of times those are the proper units that are given. But most of the time, we're going to deal with these units here, grams per cubic centimeter or grams per milliliter. Here's some density of some different substances. And again, you can see different things have obviously different density. And there's water's typical value, which is usually used. And this is from your book, I think. So, you know, we got lead, silver. They're much more dense than liquid water. I don't think it's on here. But, you know, so those things obviously would float, right? I'll save that bad joke for later. All right. Another very common way, though, that we can get the density of an object, and more specifically, that we could get the actual volume of an object, is to do what is referred to as volume by displacement. And volume by displacement basically means that when we take some water or some type of liquid like water, and we put it into something like a graduated cylinder here. Say we have an initial volume of water in there, and we take an object that we want to figure out the volume of it, like a solid object here, and we drop it in. When I drop that solid object into this liquid, will the liquid go down, up, or stay the same? Will go up, right? And we will get sort of a final reading. And the idea here is the solid object will actually displace a volume that is equal to its own volume. So if we take the difference between the initial volume and the final volume, that will represent the volume of the object. So the volume of the object can be found by basically just subtracting those two, final volume minus initial volume. And that is a really common way, especially with density, to very quickly kind of figure out the volume of a solid object. All you basically need to do is throw some water in something like a graduated cylinder, gently drop it in without breaking the graduated cylinder, and basically measure the final volume reading afterwards. So that's a very common way to figure out the volume of an object, and this is what is known as volume by displacement. So there's really three different ways that you can get a volume of an object. Again, you could just fill up a graduated cylinder or something like that, take an actual volume reading. If it's a solid, you can do some length times width times height measurements, or if you like, you could dump a solid, if possible, into some water or liquid and figure out the differences in the two volumes. Any questions on any of those differences there? All right. So that is basically what we see here, a little bit smaller to look at, but we have sort of our initial volume. They threw something in there, some zinc, it looks like. That's our final volume. And again, the difference between the two will allow us to figure out the density. So in this particular case, you might actually can see it up there, I guess, 68.6. We could put the solid on a balance and actually get the mass, which they got as 68.6. And again, they put the solid into our graduated cylinder, took two readings, and they subtracted the two here. So initially the reading was at 35.5 milliliters, and the final reading after they added the zinc to it was 45 milliliters. And again, they got the mass of it. So this gives us 68.60 divided by 9.5 gives us a density of the solid of 7.2 grams per milliliter. Now, when you calculate the density like we did here, the number always stays with the grams, and it's always 1 milliliter or 1 cubic centimeter. So it's always, the number stays with the grams part of it. Now, we did two different operations here. We basically subtracted, so we're looking at decimal places. So we should go to 1 decimal place, which is what they did here. But that 1 decimal place had 2 significant figures, which was important with the last part of the calculation, which was 4 significant figures divided by 2 significant figures. And that is why our density ends up here at 2 significant figures in terms of our answer. So you do want to keep track of the operations, the math that you do, and the sig figs until you get to the end there. If you are given a density like, say, this value here, you can use density as a conversion factor and sort of perform sort of dimensional analysis. You could say, for example, there's 7.2 grams per milliliter of this guy, or in a milliliter, there are 7.2 grams. So if we were perhaps given that value, we could use it as a conversion factor and really set it up dimensional analysis and just see the units cancel the way that you need it. Any questions on that there? All right, so why don't you give this a go? What is the density of 48 gram sample of metal if the water level in the graduated cylinder rose from 25 to 33? So what is the density of this object here? Okay, let's take a look. So obviously we're dealing with density, so you want to think about the formula. Density is mass divided by volume. In this particular case, sometimes it's really helpful just to pull out the information. So 48 grams is a mass. We have an initial volume that is 25 milliliters and a final volume after we put it in there of 33 milliliters. So if we think about our density, we already have the mass given to us. It's good to go. We don't have to do anything with it. We do need to calculate the volume here by displacement. So our volume of our object will always equal the final volume minus the initial volume. That's going to be our final volume of 33 milliliters minus our initial, which was 25, I believe, milliliters. So that is going to give us a volume of 8 milliliters in this case. We are subtracting, so we go to 1 decimal place on each. That means finally here we have everything we need for our density. Our density would be our mass, which was 48.0 grams divided by 8 milliliters. And we take 48 divided by 8 gives us 6.0 grams per milliliter here. I went to 2 sig figs because the final thing that I did was 3 sig figs divided by 2 sig figs. Yeah. And this has 1 decimal place because we added or subtracted, but it does have 2 significant figures, right? The actual number, the way it's written, which is important for the last part of the calculation. Question on that one there. So this is a very common way to figure out the volume of an object. Just basically toss it in there. Always take the final minus the initial, and you should be in good shape. All right, let's talk about another one here. Go. Obviously, as I mentioned before, we could use density as a conversion factor. So if we were to look at this, once again, we're dealing with density, which would be mass divided by volume. We are given the density here, 1.32 grams per milliliter. We are given the mass here, which is 14.7 grams. So if we just check off what's given, we have the mass, we have the density, we're looking for volume. Once again, if we rearrange it, volume is equal to mass divided by density. Now, we could do this problem more dimensional analysis and just looking at the units. As I mentioned before, the density can be used as a conversion factor. So although it is 1.32 grams per milliliter, you could flip it around and go a milliliter is 1.32 grams. So in this particular case, we could take the 14.7 grams, which is our mass. And if I want to get rid of grams, because I want to end up with volume, we're going to go opposite here, which is 1.32 grams per milliliter. The grams will cancel. That is essentially dividing what we just did there, basically just showing the units. That's going to take 14.7 divided by 1.32. That's going to give us 11.1363636 milliliters. And again, basically what we did is divide, which is exactly what you do if you just rearrange the equation. But here you can kind of see the units. Sig fig wise, we should end up where? We should end up at this one, I think is what you're saying right there, right? It's lots of ones. But this is dividing. So we got 3 sig figs, 3 sig figs should take us to there. Leaves us at 11.1 milliliters would be our volume in this particular case. Question on that one there. All right, let's do the last example here to finish it up here. I think this one's worked out. Right, there it is. All right, so John took 2 teaspoons of a cough syrup for a cough. If the syrup has a density of 1.20 grams per milliliter, and there are 5 milliliters in a teaspoon, what is the grams of cough syrup did he take? So take a couple minutes to come up with here to finish it out. Take a look since we're kind of getting to the end here. So we got a few things going on in this problem. Obviously, John here took 2 teaspoons of it. We're also given the density here of 1.20 grams per milliliter. Which we could again use as a conversion factor if we wanted to in either form. We also have another conversion sort of factor given to us in this problem, which is basically there is 5 milliliters in 1 teaspoon. Our 1 teaspoon is 5 milliliters. So in this case, we are dealing with density, obviously. We are given the density. We're actually looking for the mass here. So it does make sense in order for us to kind of get there is we need to figure out the volume basically that he took. And that is really where the volume that he took down there and sort of the conversion factor will allow us to do so. We need to use those really to turn teaspoons into milliliters so that we then could use our milliliters here in our density to get to grams. So we kind of got to get the volume to get there to figure out the mass. So we're going to just do a normal conversion here, 2 teaspoons. And once again, we're going to go opposites to get rid of teaspoons, which means we do need to use the guy here on the left. And that would be 1 teaspoon is 5 milliliters. Those guys will cancel. That will give us 10 milliliters, really is the volume that he took. Yeah. Any questions on that there? So now by doing that conversion, we do have the volume and now we have the density. So we could solve for the mass, which is volume times density. And once again, here we could kind of set it up dimensional analysis way. We're going to take our volume, which is 10 milliliters. We're going to use density like a conversion factor if you like. So we could kind of grab it here on the left so that the milliliters cancel. 1.2 grams per milliliter. Milliliters here will cancel. And that will get us 10 times 1.2. Going to give us basically that he took 12 grams of cough syrup as the milliliters would cancel. Question on that setup there. Significant figure wise, our first conversion obviously is 2 sig figs. We actually do need to look at this number here, and it has 2 sig figs, which means that is why I laid me up a decimal point there to have 2 sig figs. Lastly, here we're basically multiplying as well. So that is 2 sig figs times 3 sig figs, means we should end up with 2 significant figures when it's all said and done in this particular case. Any question on any part of that? Question on density. So you do need to know density's formula, how to rearrange it, how to solve for it. Any questions? Okay, that's going to wrap up actually chapter 2 for us.